This is an ESP32-CAM streaming live video with real-time date, time, temperature, humidity, and pressure at full resolution, without lag, without freezing. And the best part is, we are not modifying a single video frame. If you've worked with ESP32-CAM before, you already know the problem. The moment you try to draw text on camera frames, frame rate drops, the stream becomes laggy, and at higher resolution, it simply freezes. Today, I'll show you a different approach, one that keeps the video smooth, even at the highest resolution ESP32-CAM supports. Here are the components used in this project: an ESP32-CAM module, a BME280 sensor for temperature, humidity, and pressure, and a Wi-Fi connection for live streaming and time sync. That's it. No extra processors, no external display, and no heavy libraries running inside the camera loop. Before we move to the wiring diagram, let's first see how to upload the sketch to the ESP32-CAM. There are two common ways to do this. The first method uses an ESP32-CAM USB programming module. The second method is using a USB to TTL adapter. In this video, I'll show the USB to TTL cable method, since it works with almost any setup. The USB to TTL cable has 4 wires: VCC, ground, TX, and RX. Connect VCC to the 5-volt pin of the ESP32-CAM. Connect ground to ground. Now connect TX of the adapter to RX of the ESP32-CAM, and RX of the adapter to TX of the ESP32-CAM. To enable flash mode, connect I/O0 pin to ground. This puts the ESP32-CAM into programming mode. Now you are ready to upload the sketch. Once the upload is complete, remove the I/O0 to ground connection and reset the board. Next, let's move on to the wiring diagram for the BME280 sensor. Now let's connect the sensor to the ESP32-CAM. First, take a breadboard and place the ESP32-CAM module on it. Next, place the BME280 sensor on the same breadboard. Start with the power connections. Connect the VCC pin of the BME280 sensor to the 3.3-volt pin of the ESP32-CAM. Then connect the ground pin of the sensor to the ground pin of the ESP32-CAM. Now let's connect the I2C lines. Connect the SCL pin of the BME280 sensor to pin 15 of the ESP32-CAM. And finally, connect the SDA pin of the sensor to pin 14 of the ESP32-CAM. We will power the complete setup from the 5-volt rail. The ESP32-CAM internally regulates this to provide safe 3.3 volts for the sensor. With the wiring complete, let's move on to understanding the sketch. To keep things clean and stable, the code is divided into multiple files. The camera-related logic remains inside the main camera server. The BME280 sensor logic is isolated in its own module, and the browser overlay logic is handled inside the HTML and JavaScript code. Let's start with the BME280 sensor code. The sensor initialization function first sets up the I2C bus, using the SDA and SCL pins we defined earlier. Then it checks for the sensor at both possible I2C addresses, 0x76 and 0x77. If the sensor is detected, the code marks it as available. If not, the camera stream still works normally, just without sensor data. Now comes an important optimization. Instead of reading the sensor continuously, The code updates sensor values only once every few seconds. These readings are stored in cached variables. This avoids unnecessary I2C traffic and significantly reduces CPU usage. Next is the camera streaming logic. The ESP32-CAM captures JPEG frames and sends them directly to the browser using MJPG streaming. No decoding, no text rendering, and no frame modification happens here. In addition to the video stream, the ESP32 exposes a lightweight HTTP endpoint. This endpoint returns sensor values and datetime information in JSON format for date and time. The ESP32 synchronizes with an NTP server. Now let's look at what happens in the browser. The web page continuously displays the MJPG video stream. At the same time, JavaScript periodically fetches the JSON data from the ESP32 using HTML and CSS. The sensor values and datetime are overlaid directly on top of the video. Now let's see this in action. This is the live stream running at full resolution. Notice the overlay updating in real time, and the video remains perfectly smooth. No lag, no freezing, even when resolution is maxed out. This approach is ideal for CCTV projects, weather cameras, lab monitoring, or any ESP32-CAM dashboard. And because the overlay runs in the browser, it's easy to customize, reposition, or style. If you found this approach useful, hit the like button and subscribe. I'll share the complete code and diagrams below. And if you want a follow-up video, let me know in the comments. Till then, I am DHK Dude, signing off.